Hello, everyone. My name is Rojin Rezvan, and today I'm going to talk about pricing ordered items. This is based on a joint work with Shuchi, Chawla, Yifeng, Teng, and Christos, Tzamos. The problem in this paper is Bayesian revenue maximization for a single buyer, and the valuation function of the buyer is unit demand, which means that their value for any set of items is equal to their value for the highest valued items in that item in that set. In this problem, a single seller wants to sell n items in a way that would maximize their revenue. The valuation of the buyer comes from a distribution D, which is known to all parties, and it basically assigns a value to every subset of items, which is the maximum value the buyer is willing to pay for that bundle. For example, they could have a value of $1 for a cup of coffee, $3 for a cookie, and $5 for the combination. Now, a selling mechanism is basically a menu of options. For example, it could assign price of $1 to the coffee, $5 to the cookie, and it could also sell randomized allocations and lotteries. For example, it could sell a cup of coffee and a cookie each with probability half for $2. And now, just as we saw, optimal menus can sell lotteries and randomized allocations, could have unbounded menu size, and be computationally hard. So optimal menus have some undesirable properties. This brings us to the first dominant line of work, which is simple versus optimal. The idea here is to, rather than finding optimal mechanisms, we find simple mechanisms that would approximately give us the same revenue. There has been a lot of work done in this area. For example, for special classes of valuation functions, such as unit demand, additive, and sub-additive, there are constant factor approximations through simple mechanisms. For example, item pricing. And item pricing basically means assigning a price to each item, and then the price of set of items is going to be the sum of prices in that set. Note that the assumption of independence over items is necessary. And if we remove all of these assumptions, then there are examples where there's an infinite gap between optimal and simple mechanisms. So an alternate approach here is to, rather than imposing restrictions on valuation functions, we impose restriction in target class of mechanisms and compare our simple mechanisms to a smaller set and simpler objective. And this brings us to buy many mechanisms. These mechanisms are basically motivated by natural and real life examples where a buyer can go to a shop multiple times and buy any multi-set of items and pay the sum. This is what buy many mechanisms are. And if these options that the buyer purchases are lotteries, then they will get an independent draws of the lotteries. Note that for deterministic pricing, buy many constraint basically means sub-additivity over pricing. Now, before seeing the definition of buy many constraint, let's take a look at some examples. This first menu is not buy many. This is because if a buyer is interested in the bundle of coffee and cookie, they will go to the shop twice and buy the sum at the price of $3 rather than this $5. The second menu is also not buy many because if a buyer is interested in the cookie, then they could buy this lottery option twice, and in expectation, they're going to get the cookie and pay only $4 rather than the $5 here. This last menu is buy many, and that's because with no combination of some of these options, we can buy the third at a lower price and a better allocation. And with this introduction, let's take a look at buy many constraint. We say that a menu is buy many if a possibly random allocation resulting from any buy many strategy, which means being able to purchase multi-sets of items, is dominated by a single menu. And dominated here means getting a cheaper price and or better allocation. Now, what do we know about buy many mechanisms? Due to work of Chawla, Teng, and Tzamos, we know that item pricing is a log n approximation to buy many, and we know that this result is tight, meaning that if we want a better approximation, then we need the exponential size menu. So after talking about approximation, another line of work is computation. Note that if the support size of the distribution is small, then we can write the LP for optimal mechanism easily. However, this will result in impractical mechanisms with a large menu size. In fact, the size of the menu is equal to the size of the support. There are some LP duality based algorithms for larger supports due to work of Skalakis and Weinberg. However, this still results in impractical solutions. In addition to that, approximating even simple mechanisms such as item pricing is not easy. In fact, it is NP hard to do that better than a factor or square root of n, even for unit demand buyers. So what we know so far is that item pricing is an O log n approximation to by many. In specific, it's not a constant factor approximation. We also now know that computation of exact or even simple mechanisms is hard. So the question is, can we find some simple cases where we get a better approximation, for example, a constant factor approximation of optimal by many mechanisms, and at the same time be able to compute optimal or near optimal item pricing efficiently? And our approach is to look at structured values and try to find some parameter that attains the good approximation and the computation at the same time. And this brings us to the first contribution of the paper, which is totally ordered setting. In totally ordered setting, there exists a total ordering over items, and all of the buyers obey this. Which means that their value for the first item is less than or equal to the second item, and so on. We can also look at this setting as some setting of upgrades. For example, let's say I have this chair and it has some base value. Now, if I move on to this second chair, which is better than that, then my value increases or doesn't decrease, and so on for the rest of them. So we can think about it as consecutive upgrades. Now, a special case of total ordering is FedEx, which was first introduced by Fiat et al. In this setting, basically, we have total order setting with only two values. We can look at it as delivery times. And let's say the buyer wants their items delivered, and they have a deadline for the delivery. If the item is delivered before that deadline, then they get a constant value whenever it's delivered. And if it's after the deadline, then they're going to get the value 0. And FedEx setting is interesting because it is in this sweet spot between single and multi-parameter settings. So what are the results for totally ordered setting? First of all, we have shown that for a unit demand buyer in this setting, item pricing gives a constant factor approximation to revenue. So we're moving from the log n factor approximation to a constant factor approximation. Regarding computation, first of all, we know that finding optimal item pricing is strongly NP hard, even when each buyer has at most 3 distinct values. We also show a polynomial time algorithm that computes a 1 plus epsilon approximation to revenue through item pricing. And what we know about FedEx is that in the FedEx setting, optimal item pricing and optimal by many get the same revenue, and we can also compute optimal item pricing in polynomial time. Our second contribution is about partially ordered items, and here is where we define this parameterization. So let's say I want to assemble a home office, and for that I need a chair, a desk, and a monitor. Well, I am unit demand over each of these categories because I don't need 2 chairs, I only need 1. However, I can have any values over the combination of these items. The only property that it needs to have is that if I have a bundle of items and if I replace replace a chair, for example, in my bundle with a better chair, then the value of my bundle should not decrease. Now, a more general version of this is a directed forest that just defines this partial ordering, and that no 2 items, not every 2 items in it should be comparable. There should just be a partial ordering. And now the way we parameterize this setting is through width. So a width is the size of the largest set of items for which no two are comparable. In this first example, well, the width is 3 because I have 3 categories and I have total ordering through each of those categories. And in this tree, also the width is 3 by considering items 1, 3, and 7. So what have we shown about a partial ordered setting? Let's say K is the width of the partial ordering, and we have shown that item pricing gives a log K approximation in revenue to optimal by many. And regarding computation, we get 1 plus epsilon approximation to optimal item pricing when K is constant. And note that this K moves from 1 to n. Okay, so for the rest of the talk, we are going to talk about more technical parts of the paper, and we will focus on totally ordered setting, and we'll see proof sketches for the p-task for item pricing and approximation. So here we want to find item pricing for a totally ordered setting. Well, note that our valuation function is unit demand, and well, finding item pricing for unit demand buyer is not easy because changing the price of an item is going to affect the incentives and price of the other items. However, doing that in additive setting is easy because we can treat items individually and reduce the dimension of the problem. So our idea here is to somehow try and change our unit demand to an additive setting where the revenue is equal or nearly equal. Well, there's an easy way to do this, and we just need to look at our ordered values as these upgrade values that I talked about. So in the upgrade values, we have a base value V1, and the next values are simply these differences of values and upgrades between the items. And we convert the prices in the same way. Note that now the revenue from this unit demand setting and this additive setting is equal. We just need to impose this restriction that the additive buyer can only buy items in prefixes. In that way, if a buyer is interested in item I here, that would be equivalent to being interested in items from 1 to I, and the payment is going to be the same. And the other way goes as well. So, but I mean, making this conversion did not change the hardness of the problem. We have an additive setting, but we have this prefix pricing. So now the question is, what property does this pricing P need to have so that we can ignore this prefix pricing constraint, or by ignoring that, we won't lose a lot in revenue. So for the rest of this part, I'm going to talk about constant factor approximation because it better represents the idea and intuition behind it. Let's say we start from some optimal unit demand pricing P1. We round down these prices to powers of 2 in an appropriate way. And doing this loses us only a constant fraction of the revenue. And then note that once I do this, it is possible that some of the prices are equal. But for simplicity, we can assume that they're all distinct. In fact, if there are some of them which are equal, we can merge them together and just keep the one with the highest value. Well, this is because a unit demand buyer, if is presented with some items with the same price, they're going to buy the one with the highest value anyway. So doing this step is not going to affect the revenue. And now using this pricing P2, we create an item pricing P3 with prefix constraint, just as we saw in the previous slide. And note that the revenue from P3 with this prefix buying constraint over an additive buyer with upgrade values is equal to the revenue of unit demand buyer with total ordered setting under P2. And now let's say P4 is just the same as P3 except without the prefix buying constraint. Now we have 2 observations. The first observation is as follows. Well, first of all, note that P3 and P4 are all basically the difference of distinct powers of 2. Now let's say a buyer in P4, so an additive buyer, is interested in some set TJ1 to JB, with JB being the maximum index. Now, if a buyer in P3 with the prefix buying constraint wants to buy a set similar to this set, well, the cheapest way they would sell, they could buy this set is going to be this set T prime, which is all items from 1 to JB. Now, what we claim is that the price of this set under P3 is not that much far away from T. In fact, the price of T under P4 is at most twice the price of T prime under P3. And this happens exactly because of the way it is defined, and because it is each price is a difference of distinct powers of 2. Now, knowing this, using some nudging lemma, well-known nudging lemmas, because the price of P3 and P4 are close on any set, then we can conclude that there is a scaling of P4 on additive buyer that gives a constant fraction of revenue of P3. For example, a scaling of half. Okay, so now that we know some scaling of P4 gives a close revenue to P3, then, well, we know that the revenue from P3 is equal to revenue of unit demand on P2. And then this means that using this additive price in P4, we can get a revenue close to revenue of unit demand buyer within a constant factor. And finally, we can use dynamic programming to find an optimal pricing, optimal additive pricing that has a property that the prices are differences of powers of 2, distinct powers of 2, and we can also find the merged items that we did here, the grouping that we did here. So this describes a sketch for the constant factor approximation. And now I just want to point out a bit of similarities and differences from going from constant factor to PTAS. First of all, note that we do the same discretization in this setting, except rather than rounding to powers of 2, we do that to powers of 1 plus epsilon squared. And this step costs us only a factor of O epsilon. The second thing to consider here is that, well, we said that once we did the rounding, then it was possible that some of the prices are equal. What happens in the PTAS is that they might not be exactly equal, but they have the property that each of these merged group of items have close, multiplicatively close prices, in contrast to prices in 2 different groups that are multiplicatively apart. And this gives us the ability to say that then removing the constraint of prefix buying doesn't cost us a lot in revenue. Okay, so now let's focus on approximation. So here we want to approximate the revenue from optimal buy many through item pricing. Let's say P is the optimal buy many pricing, Q is the desired item pricing that we want to find, and utility of V and P is the utility of buyer V under pricing P. So the basic tool that we use here comes from the work of Chawla, Teng, and Tzamos. And basically it says that we can bond the revenue of any pricing using the differences in different scalings of the utility. Different scalings of the utility coming from different scalings of the prices. So to look at it more carefully, let's say Q is some item pricing or some pricing. Then if we scale Q by different factors, we get this concave function. And what this lemma is really telling us is that there exists some scaling of this Q, that its revenue is lower bounded by the difference in utility from scaling to different scalings L and H over some factor, log n factor. So what we want to do in this part is 3 things. First of all, we should define some appropriate pricing Q. Then we should find L and H in a way that this difference in utility between the two different scalings is some factor of revenue under P, which is the optimal by many pricing. And last, we want to find this L and H in a way that they're not that much far apart, so we get a constant factor here. Now, the way that we define the candidate pricing is that the price for item I is the cheapest way to buy item I under buy item I or better under this pricing P optimal. And for simplicity, we set H to be 1 and then try to find L. So we need to do two things. We need to find an upper bound for utility of V and Q, and a lower bound for utility of V and LQ. First of all, note that utility of V and Q is always upper bounded by utility of V and P. This is because for any set of items that we consider, it is cheaper to buy them under P than under Q, and this is because of the definition of buy many. And okay, so for finding a lower bound for utility of V and LQ, we really want it to be in this format, where it is utility of V and P plus some fraction of revenue from revenue of V and P, so that this U of V and P gets canceled out with utility of V and P here, and we remain with this factor of revenue P. To show this, we focus on one item and we try to show, we try to use the utility of some item J as a middle value to show this inequality. Now to do that, we take two steps. First, take some scaling of P, let's say beta P. Note that the difference that this scaling causes in utility of the buyer under beta P and P is really what we're going to lose from this scaling in the revenue. So this is why this inequality holds. And second, let's take a look at buyer's behavior and say lambda is the choice of buyer under P. Then, because of the buy many constraint, an adaptive buyer is not going to buy lambda more than once, and this is regardless of what item is realized in the draw and which item is instantiated. So this means that the difference in the value is going to be less than beta times P of lambda, and then by reordering this, we get this inequality. Putting these two inequalities together, we get what we wanted here. And finally, we just optimize over beta and L to get a constant factor approximation of 5.4. So to sum up, optimal mechanisms are complicated and impractical. So we opt to simple mechanisms. However, even with them, there is a unbounded gap between optimal and simple in the general case. And even for binary mechanisms, there is a log n approximation. And it is also hard to compute item pricing or simple mechanisms better than a factor of square root of n. So our approach was first go from optimal mechanisms to binary mechanisms, and then try to find a fine-grained structure that would give us something between optimal and this log n factor approximation, and in the meantime give us good guarantees on computation of item pricing. So our results going from FedEx to totally ordered to partially ordered is that, first of all, the revenue from item pricing is equal to buy many in FedEx setting. It's a constant factor approximation in totally ordered and log K approximation in partially ordered. Regarding computation of item pricing, FedEx is we can compute item pricing exactly in the FedEx setting in colonial time. We provide a p-task in totally ordered, and we provide a p-task for the constant K in partially ordered setting. And now note that all of these results are tight. And finally, this parameter K is what we had promised, and the way we parameterize settings going from FedEx, the simplest case, to the most general case. And so we basically move K from 1 to n and go from the simplest case to the most general case. Thank you.